This is the second video here about the logistic growth model. I guess I should say this right here is the logistic equation. Um, that's where it gets its name from. But so in the previous video, I worked out this equation, or this not equation. I worked out this graph of multiple solutions to this differential equation: dp dt equals blah 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 blah. In this one, we're going to solve it. Um, the carrying capacity, as we talked about in the last one, for this example is 500. Makes sense from above. And then there are three things that are sort of essential for you to be able to do to follow along with this video. One is separation of variables. That's the calculus side of it. Second is cover up, which is a method for doing partial fractions. If you have other ways to do partial fractions, that'll work too. I'm going to use cover up. And the last one is just straight up algebra. There is a ton of algebra in this example. So let's get started. At each spot, or at particular spots throughout this, I am going to point out spots where I think that decision making is important because there are so many different pathways through this. So the first step is actually one of those spots. My separation of variables, I get dp over P times 500 minus P is equal to 0.001 dt. What I think is important about this step is leaving that 0.001 on this side. If you move it over, it's going to get pretty complicated. So anytime you get one of these, leave that there. And then next thing we're going to do is write this left side a little bit differently. I'm going to write it as 1 over P times 500 minus P times dP is equal to 0.001 dt. Right side did not change. Now, the reason I did that is because this thing, it's not integratable in its current form. I need to split this into two fractions. So that's where my cover-up comes into play. So I'm just going to do some little scratch work over here. 1 over P times 500 minus P equals, well, we know that's got to be something over P plus something else over 500 minus P. So in order to do this, I cover up this. So I imagine that's not there. And then I plug in the value that makes that 0. In this case, it is 0. If I plug in P equals 0, I get a 1 over 500 minus 0. So that's 1 over 500. Now I'm going to do cover up to figure out what goes over this thing. Same thing. I cover up this spot because that is this fraction. When I do that, I plug in 500 to the remaining parts of the fraction. So I get a 1 over a 500 again. So what I'm going to do is notice this right here, it's going to get replaced with that right there. So I now have a parenthesis, 1 over 500 P over P plus 1 over 500 over 500 minus P dP is equal to 0.001 dt. You could try to integrate at this point, but this is one of those spots where you are going to take care of these guys. So my step is to take care of those. I don't want them on that left side. So what can I do? I can multiply everything by 500. On the left side, that's going to give me 1 over P plus 1 over 500 minus P with a, oh, this should be a dP. dP. And notice that's going to be a lot easier to integrate. Equals, now what I need to do is I need to take that 0.001 and multiply it by 500. For me, the easiest way to do this is to take this decimal and move it 1, 2, 3 until it gets to 1. And then I do the same decimal move here. The decimal is there, so I go 1, 2, 3. So if I multiply 0.01 by 500, that gives me 0.5 or a half. So what I get is a half dt. So now I am in a spot, finally, where I can integrate this thing. So integral. The right side's easier, so I'm going to do the left side first. I'm also going to point out another spot here where there is typically, like if there is ever a mistake in this problem, it's right here. So 1 over p. Well, that integrates to ln absolute value of p. And then the next piece is also an ln absolute value of 500 minus p. But here's where people make the mistake. People write plus. It's not a plus. It's a minus. Why is that? Because of this negative right here. I need what I have here. I need this to derive back to that. You could think about it as u sub if you want. But if I derive this without the negative, then I'm going to get a chain rule with the negative there. And then I'm not going to have a plus. So I need to put a negative here so that when I derive this to get back this, I get a double negative and a positive there. So people frequently forget that, so I'll highlight that as well. And then I get, not plus, now I got to integrate the right side. To do that, I get 1/2 t plus a constant. From here, I always call this smashing logs, okay? I guess I could have put that up here, how to deal with logs, right? But I want to smash these two logs together. Why is that? Because I need to peel away this log, this ln and this ln. And I can't do it when they're separated by a negative. But what I can do is smash them together. ln, absolute value, and I get a fraction bar. Because the minus pieces go in the bottom, that leaves me 500 minus p in the bottom. And then the positive ones go on the top, so I get a p there. So all that was a log smash. Notice if you had a plus here, then we wouldn't have gotten this fraction, so it would have been different, and that would have given you an error. The right side stays the same. 1/2 t plus a constant. All right, now you should know what comes next. I want to get to these p's right here. I guess I should say my whole goal here, I should have said this in the last video, is to find a function p of t equals, right? So that I can plug in a time and tell exactly what the population is. Really should have said that, but that's what we're doing here. So I got to solve for that p, right? Because then if I have p equals, then I know what p of t is. So in order to get there, I got to get rid of the ln. What's the opposite of an ln? Well, an e to the. And when I do my e to the, right here they cancel. And it gives me p, oops, I'll go back to green, p over 500 minus p is equal to e to the 1/2 t plus a constant. This step is one that you should be pretty familiar with. I want to write this c in a different way. So I'm going to use the e to the c thing. So e to the c times e to the 1/2 t. All I'm doing is using this plus and turning it into a minus or a multiplication outside of there. That's a common step that I've taught before, and I'm not going to go over that in detail here. The left side, in this case, stays the same, 500 minus p. Okay, so this is another spot where we are going to use the initial conditions. So I'm going to use p of 0 is 100. Paste. I'm going to highlight that here because this is the spot where you want to do it, because it makes it easy to solve for that. So what do I get? Everywhere I have a p, I write 100. 100 over 500 minus 100 equals e to the c times, all right, every time I see a t, I'm going to plug in this value of 0. So when I do that, I get e to the 0, which is just 1. So it goes away because it's multiplying. So I get e to the c is this thing. If I write over here, that gives me e to the c is, all right, 100 over 400. That's just 1/4. So that means that this right here is going to replace that right there. And I will write that down here. I get P over 500 minus P is equal to 1/4 times E to the 1/2 T. So this next step is another spot where you want to make a move that makes it easier. This 1/4, it can get really messy to deal with. So what I can do is multiply everything by 4. If I do that, I get 4P, because I multiply on the left side, it goes up top. 500 minus P equals, when I multiply on the right side, it cancels out and gives me E to the 1/2 T. So I will highlight that in blue again. Moving that up there is one of our things to make this easier. All right, so next, this is the spot where I said you need to be able to do algebra, and this trips people up all the time. And I said algebra with all caps, so it's not that crazy, but it messes with people every time. If I had the equation over here, 10x over 3 minus x equals something like 11, then the structure of how we would solve this thing is the same as what I need to do here. This p is that x, this p is that x, and then everything else is just mess in the way. What would you do? You would multiply by the 3 minus x. You would get 10x equals 11 times 3 minus x. I do that by multiplying by 3 minus x on this side and 3 minus x on this side, and these cancel, give me the 10x, and then I'm left with that 3 minus x on the right side. So that's what we need to do here. I need to multiply by the 500 minus p. When I do that, I get 4p equals, this would give me 33 minus 11x. So I'm going to do that in one step. I get this times 500, so I get 500 times e to the 1/2 t. And then I get a minus p times that. So minus p times, actually I'm not going to write it with a parenthesis, minus p e to the 1/2 t. My next step is another one where you could leave it as is, but I think it's better for us to fix this step now. These 1/2s, they're not good later, and I will explain that when we get to our final solution. So what we're going to do is multiply. Well, I'm going to divide everything by. I can actually show this in two ways. One is I am going to multiply both sides by e to the negative 1/2 t. So e to the negative 1/2 t. What that's going to do on this left side is this will cancel with that, and then it will remain on this side. If that makes sense, that's great. That's the way that I like to think about it. I like to think about as multiplying by e to the 1/2 t. But if you would rather think about, all right, let's divide by e to the 1/2 t, and divide by e to the 1/2 t, and divide by e to the 1/2 t, then notice these again cancel and cancel. I'm left with a minus p, a 500, and then on this side it's 4p over that thing. So that gives me 4p times e to the negative 1/2 t, because that's how negative exponents work. So coming from this line, I can get the same thing. Notice this, if I just reorder it, is 4p times e to the negative 1/2 t, and then equals, I have a 500 and a minus p. I'm going to stop this video here because I have a 15-minute limit, and then I will pick this up in the next video. I told you this problem was long, but we are almost there, and we're going to tie it back in with the graph from the previous video.